All right, AP Cam, if you missed office hour this morning, this is May 5th. This is your answer for question number 5. So open up that document, give yourself 15 minutes to complete this question. You can pause the video, and then when you're done with the question or the 15 minutes is up, come back to this video and I'll walk you through the answers. This problem is a great problem for periodic trends and periodic structure. If you look at your table here, they give you some data and they are asking you to interpret it. Part A, you just have to know this. What's the ionization equation for atomic fluorine? Ionization means to lose an electron. I like that they chose fluorine for this because all of your applications for fluorine in chemistry, you're running into fluorine with a -1 charge, and the student might just be tempted to go and make fluorine with a -1 charge for this equation, but that's not what you want to do. Ionization is to lose an electron, and this is the amount of energy to take that first electron from fluorine, which would make a positive fluorine. So your ionization equation looks like this. F, you start with fluorine, and it goes into fluorine with a +1 charge and then a negative electron. You don't have to have the gases here for the phase, but you'd get your point for having a neutral fluorine turning into a positive fluorine and having an extra electron. By the way, they could ask for a second ionization equation for a particular atom. If they ask for a second ionization equation, you better start with a +1, so it already lost the first electron, and then you go to a +2 charge and you'd have your electron. Or a third ionization equation, you start with a +2 and a +3, and hopefully you see that pattern there. If you wrote an equation for fluorine gaining an electron, you wrote an electron affinity equation, electron affinity. Part B, account for the fact that the first ionization energy of atomic fluorine is greater than that of oxygen. Let's look at our periodic table here. Here's our fluorine and oxygen. What happens when you go from oxygen to fluorine? Well, you add a proton, but you don't add anything to the number of shells of electrons, so we're still in the 2p subshell here. But one more proton would have a higher effective nuclear charge, so fluorine has a stronger attraction for its electrons than oxygen does, and they're at the same distance from the nucleus. That would be our explanation. Let's read their response here. In both cases, the electron removed is from the same energy level, or the same distance from the nucleus, you could say, same subshell. They list it here. That's a great thing to do, be specific. But fluorine has a greater effective nuclear charge due to one more proton in its nucleus, and the electrons are held more tightly and thus take more energy to remove. You get 1 point for a justification that connects both electrons in the same location, but one more proton attracting it in the nucleus. Part C, predict whether the first ionization energy for xenon is greater than, less than, or equal to first ionization energy for fluorine. Let's look at our table here. Xenon is right down here. So you should be thinking two things here. To move from fluorine to xenon, the effective nuclear charge for this column goes up one more. And the way to forget about xenon for a second, if we just go from fluorine to neon, we add one more proton, and that one more proton is attracted to the same shell of electrons here. And so neon would have one more effective nuclear charge, or one more attractive pull for a proton than fluorine does. And this whole column has one more than the previous element. And so xenon would have one more proton attracting it. But if you look at your shells here, we add one shell of electrons here, we add another shell of electrons here, and we add another shell of electrons to get to xenon. Xenon has 3 more shells of electrons. Fluorine is a 2p subshell. And xenon would be, count your rows, 1, 2, 3, 4, 5. We'd be a 5p for xenon. And that's a lot farther from the nucleus. So even though it has one more proton, it's 3 more shells farther from the nucleus, and we would expect that greater distance to make it easier to take the electron from xenon. So let's read their response here. They say the first ionization for xenon should be less than, that's what you need to say, less than the first ionization energy for fluorine. To ionize the fluorine atom, an electron is removed from a 2p orbital. They're being very specific, it's really close. And to ionize xenon, it has to be from a 5p, really far away. 5p is higher energy and farther from the nucleus, therefore it takes less energy. You wouldn't have to write all of this. I would just, if I was writing this, I would have just said xenon has a greater radius. It has 3 more shells of electrons, therefore the outside electrons are farther from the nucleus, and that would decrease the energy required to remove it. You get 1 point. You have to use either size or energy level or both. And the best answer would be to use both. Identify the shells and the specific location for those electrons. Okay, I want to do a side note here. and look at a couple more trends before we answer the rest of this question. So this is our first ionization energy for any atom on here. That's this equation right here. Oops. For any particular atom, start with a neutral and lose an electron. And that's the amount of energy required to do that. So for all of these, the general trend as you move to the right is it's going to increase. And it increases as you move to the right on the periodic table simply because there's more protons attracting those outer electrons, and it takes more energy to take that outside electron. And so, for example, lithium to beryllium, beryllium is going to still be in the S, this is our S block right here. It's still going to be in the 2s, so it would be 2s1 and 2s2 for beryllium. That first electron would be removed from the S subshell. But beryllium has more protons, so it's going to take more energy to remove that. And as you go up this direction, it also increases because the atoms get smaller and the electrons are closer to the attracted protons in the middle of the nucleus. But let's look at a couple exceptions to the trend here that you might need to be able to explain. So just going across our second period here, lithium goes from 520, if you can't read that, to 900 for beryllium. It increases, and that makes sense. And your justification would be, as I go from lithium to beryllium, one more proton. But look at beryllium here, from 900, amount of energy required to remove an electron, to 800. It decreases for boron. Well, that doesn't make sense because boron has one more proton. And wouldn't you say that the one more proton in boron would attract the outside electron more, and it should be higher than beryllium? Why does it decrease? Well, let's look at our next row. Sodium, 500 to 700 increases. That makes sense, one more proton. Magnesium, 700 to 600. So it gets easier for aluminum. This whole row right here, I'm sorry, not row, but column, which we call groups or families, has lower energy required to remove the electron. Why? Well, that electron is in a p subshell. So let's just look at beryllium and boron. Beryllium is the 2s. It'd be 2s1. And over here, our first electron that we would remove is the 2p1 for boron. Well, if you remember your shapes, this is a spherical shape, and this is that dumbbell-shaped orbital. And the dumbbell-shaped orbitals are farther from the nucleus. They're a little bit higher energy, farther from the nucleus than our S subshell, and that makes it easier to steal that outside electron for the first P1. But then when you get to carbon, it continues to increase. Why? Because we keep adding protons, so it gets harder and harder as we go across this way. We add more protons. So this column is an exception to that. There's one other column that's an exception to that, and it's this column right here. It's a very small decrease for this column, and that's your oxygen and sulfur and selenium. Because you have electron-electron repulsion. So nitrogen, the first electron is easier to steal than, or harder to steal than oxygen, because if you look at your P block, let's draw this. My P block for oxygen, it has 4 electrons in the P, 2p4. So we have 1, 2, 3, and that fourth gets paired up. And that first electron, because of that repulsion, there's 2 electrons in the same dumbbell. They're sharing the same dumbbell shape here. Those electrons are repelled by each other. And so if I want to take the first electron, it's going to be one of these electrons that are easy to take, and it decreases your ionization energy only for the first electron. Then your second electron for oxygen would be a lot higher. So there's your exceptions for ionization energy. I want to show you one other thing here, connection, electron affinity. And your electron affinity equations, let's just choose nitrogen here. Nitrogen's electron affinity equation would look like this. You take neutral nitrogen, and affinity is to take an electron. So we'd have a -1 charge here, and our plus electron would be on the left side. So getting an electron added to nitrogen, it'd make the -1 charge. That's what it means by electron affinity, the attraction for the electron. And this would release energy. If you look at the numbers on this little table here, it's the amount of energy that gets released by absorbing an electron. Let's look at some exceptions to our trend here. This column right here, they're all 0. Why are they 0? There's no energy release. Another way to say that, there's no attraction for an extra electron in that column. Well, all this column has a full subshell. And that full shell means that next electron would have to be in one shell farther out from the nucleus, and there's going to be no attractive pole for that electron in that next shell. Okay, let's look at another one over here. What happens if you had to justify why these first couple have really low ionization or electron affinities? Well, this is the S block. The S block gets filled. The next electron would have to be in the P block, and it's a little bit farther, just like we talked on that last slide, from the nucleus. And so with the full S subshell and not quite enough protons like boron has, it doesn't have a strong enough attraction to get one more electron in that next subshell, the P subshell. How about nitrogen? Why is it lower than my oxygen. Well, the nitrogen would have that p block filled up like this. Nitrogen has 1, 2, 3 in the p block. That next electron would have to pair up with one of these, and that's going to create that same repulsion we talked about right here in the orbital, and so it's not going to have a strong attractive force for that extra electron. How about these ones? These are all 0. What would your justification be here? And this is the type of thing you should be thinking about. How do I use periodic trends or my knowledge of electron structure to explain something? Well, you could take a great guess here. This is a full D subshell, and that means we're going to have a D10. It's going to be completely filled. There's no extra space for electrons here, and these particular atoms just don't have enough attractive pole in the nucleus to attract one more electron in that P subshell. How about manganese? What does manganese look like? Well, manganese has a D subshell, 1, 2, 3, 4, 5, so this would be a D5. Well, that's a half-filled D subshell. So the same explanation we just used for nitrogen here to explain why it's low, manganese with a half-filled D subshell can't attract one more electron and get that electron-electron repulsion in that D subshell either. So those are your explanations, kind of some extra trends there. Let's look at our drawings. I'll just jump right to our structures. If you drew your structure for xenon like this, for your xenon trioxide, you would get your points. If it looks like this, you get your points. You get 1 point for the correct structure for both of them. So they both have to look like this for your points. And if you accidentally forgot a lone pair of electrons, you would miss 1 point one time. So maybe I forgot a lone pair of electrons here, and I forgot a lone pair of electrons here, you would miss only 1 point on that problem. You still get 1 out of 2. E, you won't have these questions on the test this year, I would expect anyways, because this is way too easy to look up on a table. But this table is worthwhile to have handy still. And the reason being is because you could use this in an explanation for why something's polar or nonpolar. And you could say it's trigonal planar, or it's linear, or it's angular bent, therefore it's polar. And you can use that in your explanations if you want to, because the people who are reading the test will have a good understanding of what you're referring to if you refer to geometry. Part II, we don't do hybridizations in the D, but we do hybridizations up to the P. So you could have been asked about this xenon, and you'd say it's an sp3. There's 4 locations of electrons around it. Here's 1, 2, 3, 4, and we always fill us up. The first one's the S, that's 1, and then we can do up to 3 in the P, and we need 4, so that's how we get sp3. We need 4 locations of electrons around it. Our last one, predict whether it's polar or nonpolar. I want to walk you through this one. This is a great kind of write down this and be ready on the test for justifying polar and nonpolar with this terminology. So if I was reading this and I was the grader on the test, this is what I would be looking for. The xenon trioxide molecule would be polar. Okay, they got that right. Because it contains 3 polar bonds, check. I'll be looking at this, that's good. That are asymmetrically, check, they've got it, I'm done, I gave them full points. Asymmetrically arranged around the central atom. What are we looking at here? I would write down these 2 terms for justifying polarity of molecules. You must have polar bonds in a polar molecule. And you must have asymmetrically arranged atoms around the central atom, or asymmetrically arranged bonds around the central atom. If you wanted to justify why something's nonpolar, you can use these exact same terms. If I go back up to this molecule up here, and if they asked me about this one, I would say it's nonpolar. I would still say it has polar bonds, but all locations of electrons around the central atom are symmetrically arranged, therefore it's a nonpolar molecule. In other words, if I draw a line through this way, it's perfect symmetry. If I draw a line through this way, it's perfect symmetry. This way, it's perfect symmetry. So that symmetry allows this molecule to be nonpolar. That's what you want to refer to. You want to refer to, are the bonds polar or not, and is it symmetrically arranged? And that's the terminology you should use to get your full points on that type of problem. So here's your point values. 1 point is earned for the answer is consistent with the shape indicated in part E. That means if you drew it like this, you would say polar. But if you drew it some other way, maybe you had xenon in the center like this and you forgot those extra electrons, and you have a trigonal planar arrangement, you would say nonpolar. So if you're consistent with what you drew, and then 1 point for an explanation that correctly relates to shape. That's these 2 terms. You have polar bonds, and it's either symmetrical or asymmetrical. That's your other point at the end there. So here's your point values for 5. The average was 4 out of 9 points. If you beat that, good job. You should be feeling well for your AP test. Okay. I want to give you one more recommendation. If you have that test still pulled up, I won't work through the parts here, but this would be a great kinetics practice problem for looking at a data set and determining the rate law for a chemical reaction with units. So I would do this problem if you have a little bit of extra time. And I hope that helped working through this problem. Continue to review for your test this year, and see you later.